Okay, hello everybody. So let's talk about the binomial distribution. So often we're interested in the number of a specific event occurring out of, say, a set number of trials. The trials in a binomial distribution are Bernoulli trials, which means they are trials in which there are one of two outcomes, success or failure. And they're independent, so they're independent Bernoulli trials. We may have, for instance, a flip of a coin 10 times, and we say out of that 10 flips of a coin, how many times do we land on head? So that would be, the heads would be success, so the number of heads would be what we're looking for in that case. So for a binomial random variable, the probability of a given number of successes is n choose x. So this is what we call a binomial coefficient. N choose x is how many different ways can we get x outcomes in n trials. And this is p is the probability of success raised to the xth power. So say if p is 0.5 in the flip of a coin. X is the number of successes we're looking for, like when we have 0 successes, 1, 2, 3 successes, in that case being a heads, that's what X would be, and then 1 minus P is the probability of failure. Since success and failure are mutually exclusive, so they must add up to 1, so if the probability of success is P, the probability of failure is 1 minus P. Sorry for all the noise here. I live in a noisy area. That's just the way it goes. So here we have this is the probability mass function, but it must sum to 1. So in probability, the probability of all possible events, mutually exclusive events, it means they can't occur together, has to sum up to 1. When our variable is discrete, as in the case of, say, a flip of a coin or whatever we're counting, it's a probability mass function, so we can sum it up. So in this case, we're summing from x equals 0 successes up to n successes. The function is n choose x, p to the x times 1 minus p to the n minus x. Now, we've got to keep in mind there's also a binomial expansion, and you can certainly look this up. There's many different ways that we can convert what we call a binomial here, because there's two different variables, a and b, right? Raised to the nth power, so we have n number of events. So if we do a binomial expansion, that becomes the summation from x equals 0 to n choose x, a to the x, b to the n minus x. So this is something that's interesting. I urge you to look it up. There's good videos about binomial expansions everywhere. The Khan Academy has a really good video. You can look at how a binomial expansion is done, either just through the regular process or using Pascal's triangle. We can achieve this, but basically it ends up being what we have here. So we can use this knowledge to convert our binomial into this a plus b to the n, and we do that. Okay, so we want to prove that the summation of all possible values of the binomial equals 1. So if we go from x equals 0 to n trials, we have n choose x, p to the x, 1 minus p to the x. This is our PMF, probability mass function. So in this case, using the binomial expansion, so we have here p is equivalent to a, 1 minus p is equivalent to b, so we get a plus b, so p plus 1 minus p raised to the nth power. So p plus 1 minus p, well, you got p minus p is 0, so we get 1. 1 raised to the n is 1. We have therefore proven that this is the appropriate probability. This is a valid probability mass function. So let's go ahead then and calculate the expected value. The expected value is the mean, or mu. Unlike what I did with the Bernoulli random variable, I prefer using the moment generating function. It's just easier for me. you may like using the just working with the variable itself. I like the MGFs. So the first moment of any distribution is its mean. The second moment can be used to calculate the variance, and so on. So for the moment generating function, if we set t, the value t, to 0, we'll actually get what's known as the slope, but the slope is equal to 0 in this case. So the derivative of a function is its slope, but if we set it to 0, a 0 slope means it's either a maximum or a minimum, and that's what we need in order to calculate the average value here. So we have the moment generating function. So that's the expected value of e to the tx. So this is e is an exponent, right, to tx. So it's Euler's number actually in this case, 2.7 something. Sorry, I'm not perfect in remembering what Euler's number is, but hey, that's life. So in this case, when we calculate any expected value, it's whatever we're looking at. Like usually we do expected value of x would be x times p of x, which is the probability mass function in this case. But since we're doing e to the tx, so it's e to the tx minus the probability mass function. So we get, and I eliminated the x equals 0 to n here just for simplicity. So we get the sigma. This is a sigma. That's what that symbol is. So we got sigma e to the tx times the PMF, which is n choose x, p to the x, 1 minus p to the n minus x. So what we can do is we can simplify this a little bit here and put these together, since they're both have powers associated with them. So we get p e to the t to the x times 1 minus p to the n minus x. So now we have a and b right here, right? So we can go ahead and use that binomial expansion. So we get a is p e to the t, and b is 1 minus p. So we get p e to the t plus 1 minus p to the n. Well, we take its derivative. So this is its MGF, moment generating function. We take its first derivative. So we get, well, we go multiply. This is like any derivative. It's n times whatever's here to the n minus 1 power, and then we take the derivative of what's inside this function here. So with respect to t, so it's PET, and its derivative is PET. Then we set t to 0 to find the mean. So we get, well, if t is set to 0, you get PE to the 0 power plus 1 minus p n minus 1 times, again, PE to the 0 power. Let's go to the next figure. All right. I think that's it, right? Nope. Here it is. All right, so let's go to this next figure. Increase the size here. Set equal to 0, so t becomes 0, so we get n p plus 1 minus p to the n minus 1 times p. So well, here we got p minus p is 0, so this is 1. So we got n times 1 times p, we get n times p, so that is our mean for the binomial distribution. So that tells us what's the probability on average in the long term. The number of successes we are to have is n times whatever the probability is. If it's 0.5 and we want to know how many heads we'd have out of 10 trials, it would be 10 times 0.5, right? So it'd be 5. So on average, it gives us what the expected value is. So we have to calculate the variance as well. Now the variance is the second derivative with respect to t minus the mean squared. So we've got to remember that it's minus the mean square. So we can go ahead and calculate the second derivative, but then at the end we have to subtract the mean squared. Well, the second derivative, well, we take the first derivative, and then we do the second derivative. But that first derivative is a product. So in that case, we have one part of the product is n times p e to the t plus 1 minus p to the n minus 1 times p e t. So this is a separate piece here. So we actually have two different pieces here. So we go ahead and use the product rule. So the product rule states that the derivative of the product of two variables, like for instance, or two functions, a variable is a function anyway, right? F of x times g of x is f of x times g prime of x plus g of x times f prime of x. So if we let n p of t 1 minus p to the n minus 1 equals f of x, then p t equals g of x, so we can just plug that into this equation here. So if f of x, so we copy that right here, right? Here it is, f of x right here, times the derivative of g of x, so the derivative of g of x. So g of x is PET, its derivative is actually PET, so this isn't that horribly difficult, times g of x, again it's PET, times the derivative of f of x. So f of x, again, we have here is this value here, so the derivatives, we're going to multiply this here, right, bring this down, so it's n times n minus 1 times what's in here, PET 1 minus p, right, to the n minus 2. So we always subtract 1 from that. And then we take the derivative of the inner piece here, which is the only one that has t is PET, so that's again PET. So you'll see the second derivative, we have nPET plus 1 minus p to the n minus 1 PET plus, so the second part here is g of x times f prime of x, so we get PET, right, that's g of x, times the derivative here, so we get n times n minus 1, so we're taking all, get n, bring that here, n times n minus 1 times what's in here to the raised to the n minus second power, and then we have to, yeah, so that, then we have to actually do another PET because we're taking the derivative of what's inside, which is PET with respect to t. So now let's rearrange that to simplify. So we get nPET 1 minus p to the n minus 1 times PET. This stays the same. Here we have 2 PET, so that's PET squared. Everything else stays the same. And there we go. So now we set this equal to 0. So all the t's become 0. So we get n, and since this is 0, that's PET, so this ET becomes 1, so it's PET, e to the 0 equals 1. So it's p plus 1 minus p to the n minus 1, which is 1. So that's what we get the 1 here times PET. Well, e to t is 1 because t is 0, so we get p. So this is that first part right here, n times 1 times p. Second part here, you got t is 0, so this e to the t becomes 1, so you got p squared. You get n times n minus 1, that stays the same. PET becomes p to the e to the t becomes 1, so this is 1. This is basically 1, so we get 1. Simplify this further, we get n times p plus p squared n minus 1, so we get np plus p squared, n times n is n squared, minus p squared n, because that's p squared n times 1, right? So the variance of x would be this value minus sigma squared. So sigma, if we, mu squared, so the mean. So the mean was n times p, so now we get n times p squared. So we take this value here, which is the second derivative of the moment generating function set to 0. So we get np n p squared n squared minus p squared n minus np squared. Well, np squared is n squared p squared, but we have that here. Basically, these two are the same, so they cancel out. So we get np minus np squared. Well, np minus np squared is the same as np. Well, we pull out one n and we pull out a p, so we get np times 1 minus p. So 1 minus p is the opposite of success, the probability of failure. We get np times 1 minus p as the variance for the binomial distribution, and its standard deviation is the square root of sigma squared, so it's np times 1 minus p. We are done, baby. This is awesome. I love doing this stuff, and I hope you enjoyed it too. Sorry for all the noise, but I live in a noisy neighborhood, and that's the way it goes. But, you know, the math stays the same, and so does statistics.